Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
Office networks often have many devices, and with that comes many IP addresses. We don't want to manually configure every single device with its own IP address though. We also don't want to reconfigure every phone, tablet and laptop as they roam through the building. The solution then is to automate the process of handing out IP addresses. This is what a DHCP server can do for us, so we're going to see how it works and how it's configured. For a computer that's turning on for the first time, it won't have an IP address. A DHCP server can help with this, but our new computer doesn't know where to find it. So it creates a special DHCP discover message. It then broadcasts this message out to the network. This message contains the computer's MAC address. Regular devices will see the packet and ignore it. DHCP servers, on the other hand, will be very interested. The DHCP server contains a database or pool of IP addresses that are valid for the local network. So when it receives the discover message, it knows that the new computer needs help. It looks in the address pool, it finds an available IP, and it temporarily reserves it. It will then put this information in a DHCP offer message and send it back to the client. Sometimes this is sent as a broadcast, and sometimes as a unicast message. The reason why is a bit too complicated to go into now, but if you're interested in finding the answer yourself, have a look at RFC 2131. What happens in a case like the one we're showing here, where there is more than one DHCP server? Well, the client will get more than one offer. So in our example, a client has received two offers. It will select one and formally ask permission to use it by broadcasting a DHCP request message. The server finishes up the process by sending a DHCP acknowledgement message to the client. This is where the server officially allocates the IP address. The client is now free to use the IP and any other information that the server may have given it. We'll cover the extra information soon. Requesting an IP from a DHCP server is a 4-message process. If you want an interesting way to remember this process, just think of Dora the Explorer. We've been talking about a dynamic allocation of IP addresses. We also have the option of a static allocation. This is also called a reservation. This is where the DHCP server is configured to give a specific IP address to a specific client. The client is identified by its MAC address. So when the discover message comes in, the server sees the client's MAC address, knows that it's meant to give this particular client a special IP, and puts that IP into the offer message. There are a few cases where you might want to use this, but they're not too common. See if you can think of a few cases where you might want to use this feature and put them in the comments. When a DHCP server sends the offer message, it will also send a lease time. This is the time for which the IP address is valid. Windows servers, for example, will offer a lease of 8 days by default. Cisco DHCP servers, on the other hand, have a default of only 1 day. Of course, we can set these values to whatever we need them to be. By the way, if you're interested in digging deeper into the DHCP message format, I'll put a link in the description that you can have a look at. If the lease were to expire, the DHCP server will put the IP address back into the available pool. The alternative is that the client may want to renew the lease. It will attempt to do this halfway through the lease period. So with a Windows server, for example, the client will try to renew after 4 days. The server will try to be nice to the client. It will try to let it keep the IP it already has. However, there is no guarantee, so the client may end up with a completely different address. A client may choose to send a release message to the DHCP server, saying that it's finished with using this IP. This is not a requirement though, so it's completely okay if the client doesn't give the IP back when it's done. If you're working with Windows, here's an issue to be ready for. Sometimes a Windows machine will have an IP address like this one, starting with 169.254. This is called an APIPA address and usually happens when this machine could not get an address from the DHCP server. To force Windows to try again, we can run ipconfig/renew. Often we use the release and renew commands together. This is useful, for example, if we have updated our DHCP server with some new information and we want the client to get a fresh IP. But DHCP servers aren't just good for handing out IP addresses. They can also hand out extra pieces of information called options. There are many different options that can be configured, but there are a few common ones we should discuss. The router option gives the client the IP address of the default gateway. The DNS server option tells the client about DNS servers on the network. We're going to talk about DNS servers in the next video. The domain name option tells the client which domain it's a part of. For example, networkdirection.net. This is quite important in Windows environments. And finally, the TFTP server option gives the client the IP address of a local TFTP server. We won't get too deep into TFTP, but this is a server that transfers small files. For example, we can back up our switch and our router config files to a TFTP server. This is critical though when you have phones on the network. When the phone starts up, it gets an IP address and TFTP server addresses through DHCP, and that's where it downloads its config files from. Well, we've gone through quite a bit so far. You can use these questions to see if you've understood what we're talking about. We've seen that the DHCP process starts with a client broadcasting a discover message. Can you see the problem that we could face here? Broadcast messages are only useful on the local LAN segment. This is because routers do not forward broadcast messages. When a client broadcasts the discover message, it will not reach the DHCP server. So when we have several LAN segments in our network, how can we provide DHCP services to them all? Well, one option is that we can put a DHCP server in every LAN segment. Or maybe we could give our DHCP server a network card that connects to each LAN segment. And we might do this in some parts of our network, but that adds up as a lot for us to manage. The simple alternative is called a DHCP relay. We can configure an interface on a router to act on the DHCP server's behalf. When a client broadcasts a discover message, the message reaches the router that is configured as a DHCP relay. The router is configured with the IP address of the remote DHCP server, so the relay will then send the message directly to that server. The server responds to the message by sending the offer to the router. The router then forwards this on to the client. This is a very efficient method, as we can have a server with all the DHCP configuration in one single place. You will regularly find DHCP servers running on Windows, so I'd like to give you a brief look at how it's configured here. Here we have the DHCP console, just after the DHCP role has been installed. We're going to create a new IPv4 scope. The scope is just the Windows name for the DHCP pool. Naturally, Windows has a wizard for this, and we start by giving our scope a name. Next, we configure the first and last addresses in the pool, as well as a subnet mask. Usually we don't want to hand out all addresses in the range, so now we can configure exclusions. These are the IPs that we don't want handed out dynamically. And now we can configure the lease time. By default, this is 8 days on Windows, but just for fun, we'll set this to 4 days. We can now configure extra options that we can hand out to the clients, so we might as well do that now. First, we configure the default gateway. This is the router option. Now, the domain name and DNS servers. There's a DNS server in here by default, but we can add more if we want. Our DHCP server will try to contact the DNS server to confirm it's up. It's not available from our lab environment, but it still lets us add it if we want. As this is a Windows server, we can add Wins servers if we want to. This is a relic of the old days, and for most part we can completely ignore this now. And finally, we can choose to activate the scope now or later. So why not now? Inside the scope, we can see the address pool. And in here we can see any leases. This is any IPs which have been handed out to our clients. Our server hasn't handed any out yet. We can also create a reservation if we want. This, as we discussed earlier, is if we want to reserve a particular IP for a particular device. For this, we need a name, an IP address, and a MAC address. And it doesn't look like Windows likes the format that I'm using, so hang on a sec, let's try a different format. It doesn't like that either. It looks like it just wants letters and numbers, which I guess that's fine, I suppose. And finally, we can see the scope options that we configured earlier. Now, let's try and make this more interesting, and we'll try to configure this on a few Cisco routers. Here we have a small topology with 2 networks, 2 routers, and 2 workstations. R1 is going to be our DHCP server, and it will need to hand out an IP address to workstation 1. Workstation 2 will also need an address, but it's on a different subnet, so we're going to have to configure R2 as a DHCP relay. So let's start by configuring R1. The first thing to do is to define a pool with IP DHCP pool, and then give it a name. This is exactly the same as the scope we saw earlier on the Windows server. The next part is to configure the network. This is the network address and subnet mask that makes up the addresses in the pool. We can't configure a specific start and end address like we did in Windows. The default router is the IP address of our default gateway, so we'll choose 172.16.10.2. And next, the lease. We'll choose 4 days in our example. The domain name is quite self-explanatory, as is the DNS server. The next server is a bit more interesting, and its function may not be immediately obvious. This is used to configure a TFTP server, which we talked about earlier. So this is the part we need if we want to give phones their configuration files automatically. And that's it for the pool itself. But there is still something else we need to do, and that is to tell the router which IPs should not be given out, using the IP DHCP excluded address command. We need to take care not to allocate an IP address for anything that's static, like our router's IP address. If we don't think about this, we face a potential IP conflict. So if you have servers and printers with static IPs, make sure you exclude these IPs from the pool. Now we should test it out on workstation 1. Usually a workstation like this would request an IP address while it's booting. In this case though, the workstation already booted before DHCP was configured. So we'll use the dhclient Linux command to request an IP address. The -v gives us more information so we can see the entire process. Interestingly, the request and offer are displayed in a different order here, but we can still see that we're being given an IP address, and we can see the server that gave it to us. Now, are you ready for something really interesting? Back on the router, we have a console message which says that there has been an IP conflict. The router tried to give out 172.16.10.2, but this is already in use by R2. Fortunately, the router was able to detect this and give out a different IP address instead. It's great that R1 discovered this automatically, but we could be in trouble if, for example, R2 had an ACL that blocked lots of different traffic types. If R1 cannot detect that there's a conflict, we would definitely be in trouble. So we're best off adding this IP address to the excluded address range. We need to configure a pool on R1, and we need to configure the DHCP relay on R2. We'll stick with a very simple pool in this case. This shows that most of the configuration we used earlier is optional. Now to configure the relay. On a Cisco router, we use the IP helper address command, and we use this on the interface that will be receiving the discover messages. If we try the same command on workstation 2, we can see that this is also successful. Notice that the offer seems to be coming from R2 and not R1. That's because it is making the offer on R1's behalf. There are 3 verification commands which are very useful, especially if you have troubles getting DHCP working. Firstly is the Show IP DHCP pool. This shows pool statistics, including pool size and how many IPs have been allocated. It is possible to run out of IPs, so keep an eye on how many IPs are left. Next, we have Show IP DHCP binding. This shows a list of each IP address that has been allocated. Let me just make this window a touch bigger so it all fits in a little better. And here we can see the IP address that has been allocated, the MAC address it lines up to, and the date that the lease will expire. And finally, we have Show IP DHCP server statistics. This one is very useful for detailed troubleshooting. We can even see the message types and how many have been sent and received. And here are 2 more questions for you to test your understanding on. Of course, you can have more complicated.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.